Hello, I'm Achut Nair from Nair's Aviation Ground School. This is the 27th video in a new series of educational aviation videos for the aspiring pilot. As noted in previous videos, the airplane is a machine that is much at the mercy of the natural forces. In addition to wind, another very important determinant in the performance of the airplane is what is known as visible moisture in aviation parlance, but actually refers to the possibility of ice. This video is about aircraft icing. Aircraft are very susceptible to environmental effects. One of the most hazardous of these effects is icing on the aircraft surface. In-flight airframe icing occurs when supercooled water freezes on impact with any part of the external structure of an aircraft during flight. Although the nominal freezing point of water is 0 degrees Celsius, water in the atmosphere does not always freeze at that temperature and often exists as a supercooled liquid. If the surface temperature of an aircraft structure is below zero, then moisture within the atmosphere may turn to ice as an immediate or secondary consequence of contact with the aircraft surface. The size of the supercooled water droplets and the nature of the airflow around the aircraft surface determine the extent to which these droplets will strike the surface. The size of a droplet will also affect what happens after such impacts. For example, larger droplets will often be broken into smaller ones. Any cloud containing liquid water can present a significant icing environment if the temperature is 0 degrees Celsius or less. Any drizzle or rain which is encountered at temperatures of freezing or below is likely to generate significant ice accretion in a very short period of time, even if reasonable visibility prevails, and such conditions should be exited by any appropriate change of the flight path. Snow, in and of itself, does not present an icing threat, since the water is already frozen. However, snow can be mixed with liquid water, particularly cloud droplets, and in some circumstances can contribute to the accumulation of hazardous frozen deposits. Airframe icing can lead to reduced performance, loss of lift, altered controllability, and ultimately stall and subsequent loss of control of the aircraft. Hazards arising from the presence of ice on an airframe include adverse aerodynamic effects and the blockage of the pitot tube and static ports. Ice accretion on critical parts of an airframe unprotected by a normally functioning anti-icing or de-icing system can modify the airflow pattern around airfoil surfaces such as wings and propeller blades, leading to loss of lift, increased drag, and a shift in the airfoil center of pressure. The latter effect may alter longitudinal stability and pitch trim requirements. Longitudinal stability may also be affected by a degradation of lift generated by the horizontal stabilizer. The modified airflow pattern may significantly alter the pressure distribution around the flight control surfaces, such as ailerons and elevators. If the control surface is unpowered, such changes in pressure distribution can eventually lead to uncommanded control deflections which the pilot may not be able to overpower and control. Partial or complete blockage of the air inlet to any part of a pitot-static system can produce errors in the readings of pressure instruments such as altimeters, airspeed indicators, and vertical speed indicators. The most likely origin of such occurrences to otherwise serviceable systems has been the non-activation of the built-in electrical heating, which these tubes and plates are provided with, although in some cases the detailed design of pitot heads have made them relatively more vulnerable to ice accretion even when functioning as certified. It is now also recognized that the effects of high-level ice crystal icing can have what are usually transient effects on the effectiveness of normally functioning pitot probe heating. Ice secretion on aircraft surfaces can be distinguished as rime icing, clear or glaze icing, and or a blend of the two referred to as cloudy or mixed icing. Rime ice is formed when small, supercooled water droplets freeze rapidly on contact with a sub-zero surface. The rapidity of the transition to a frozen state is because of the droplets are small and that almost instant transition leads to the creation of mixture of tiny ice particles and trapped air. The resultant ice deposit formed is rough and crystalline and opaque, and because of its crystalline structure is brittle. It appears white in color when viewed from a distance, for example from the flight deck when on a wing leading edge. Since rime ice forms on leading edges, it can affect the aerodynamic characteristics of both the wings and horizontal stabilizers, as well as restricting engine air inlets. Rime may begin to form as rough coating of a leading edge, but if accretion continues, irregular protrusions may develop forward into the airstream, although there are structural limits to how much of a horn development can occur. Clear or glaze icing is formed by larger supercooled water droplets, of which only a small portion freezes immediately. This results in runback and progressive freezing of the remaining liquid, and since the resultant frozen deposit contains relatively few air bubbles, as a result, the accreted ice accretion is transparent or translucent. If the freezing process is sufficiently slow to allow the water to spread more evenly before freezing, the resultant transparent sheet of ice may be difficult to detect. The larger droplets and slower the freezing process, the more transparent the ice is. Mixed or cloudy icing, the blend of the two accreted ice forms in the wide range of conditions between those which lead to mostly rime or mostly clear ice, and is the most commonly encountered form of icing. Its appearance will be determined by the extent to which it has been formed from supercooled water droplets of various sizes. The aerodynamic effects of accreted ice on the continued safe flight of an aircraft is a complex subject because of the many forms such ice buildup can take. In certain circumstances, very little surface roughness is required to generate significant aerodynamic effects, and as ice load accumulates, there is often no aerodynamic warning of a departure from the normal performance of the aircraft. Stall warning systems are designed to operate in relation to the angle of attack on a clean airplane and cannot be relied upon to activate usefully in the case of an ice-loaded aircraft. Icing on aircraft can and have led to accidents. The most common icing related accidents occur in smaller general aviation aircraft. General aviation aircraft that are not equipped with ice protection systems but are flown in icing conditions may encounter enough icing at cruise altitudes to overwhelm the aircraft power reserve, leading to an inability to maintain altitude or airspeed. In mountainous terrain, this very often leads to a stall, followed by a loss of control when the pilot attempts to maintain altitude over the high terrain. Alternatively, a collision with terrain may result when altitude cannot be maintained. Regardless of the type of terrain, any aircraft without airframe ice protection systems, which are flown into icing conditions, can quickly encounter a stall, which leads to loss of control due to the excessive drag and loss of lift which ice buildup can bring. Icing might seem like a factor that is of little importance, but airplanes fly in multiple different temperatures during the course of even a short flight. Understanding where and when icing can occur allows the student pilot to anticipate their actions in advance and aids in proper aeronautical decision making. Icing is a major factor to consider when planning a flight. It should not be taken lightly. For more information, please contact us at liftanddrag@gmail.com, and please visit our website at nyersaviation.webnode.com. Thank you, safe flying,